have Mariana Jaber talking about cosmic tension solutions through using dark matter and ISW-void.
Thank you. Thank you to the organizers for putting together such a lovely meeting and bringing so many ideas for discussion here. I am based at the Center for Theoretical Physics in Warsaw, and I'm bringing work that's done in collaboration with members of my current group and some other postdocs I will acknowledge. So right, in this paper, we just published recently this year, which was led by Krishna Naidu, a former postdoc in our group, and my current PIs, Wojtek and Maciej, as co-authors. We proposed a solution that can potentially put together the H0 and sigma A tensions with a single modification to the Lambda CDM model. And I'm going to explain the phenomenology behind this idea. Furthermore, this paper has been continuated as a master thesis project for a student, Magdalena from the Jagiellonian University of Krakow. There's been enough of discussion in these days about what an incomplete picture we have in Lambda CDM, meaning that we lack the fundamental physics and understanding of its ingredients from first principles. It's perhaps not needed to emphasize more that we lack the proper models that acknowledge how the dark sector in particular could be described, without touching upon on the very nice review we had today in many other ways that we could extend this paradigm. On the one hand, we know, and we have the need to include this dark matter ingredient to be able to understand a number of observations that go from galaxy rotation curves to the bullet cluster or many more other observations, and yet we lack the fundamental detection of this component. We haven't seen this particle in our experiments yet. And even more, we don't understand whether this could be a single particle, a whole sector of interacting particles, maybe Bose-Einstein condensates, or even more exotic ideas, right? So there's a lot of unknown physics that we could investigate in this regime. Without going further, same goes for the dark energy component that we put in a model just by the simple addition of a cosmological constant with all of the theoretical complexities and challenges that it brings, even if we really do not address those theoretical problems from the cosmological constant when we modify this sector. Wojtek already gave a very nice talk about other ways of extending these assumptions that we take in the model, in the Lambda CDM model, in particular going towards modified gravity theories, but importantly, the difficulties of testing these ideas when compared to observations. So I'm not going to dwell on that. I think we can all agree that despite all of those deep unknowns and theoretical issues, Lambda CDM has shown an incredibly success in explaining the bulk of information and observations that we have gathered across the decades, with the exception of the few cracks on it, which I refer as cracks to those tensions and anomalies that we are here discussing in this conference. The most obvious one, the most prominent one, and perhaps the most discussed one is the Hubble tension because of the statistical significance that it has reached. So this is gathering a lot of interest in how can we understand the mechanism behind this anomaly, this tension that we see in our data. Equally important, like we just saw in the previous talks, the tension that we have in the S8 parameter or the sigma 8 parameter, with a statistical significance perhaps not as high, but equally important and deserving of attention. Perhaps a less known or discussed anomaly is the known integrated Sachs-Wolfe void anomaly, or the ISW-void anomaly, which refers to a mismatch between the expected value and the observed value of voids and stacked voids and their cross-correlation with the CMB photons and their temperatures. In general, what we observe is higher. The signal that we observe is higher than we would expect or model in simulations. How much this signal or this discrepancy actually is found depends on the sample of the voids that you use to stack and then measure it. Crucially, it depends basically on whether you identified your voids on a spectroscopic sample where you can identify with some sort of spherical void finding, so your voids are rather small, and you can see that the mismatch between what you would expect in Lambda CDM and the observed values is of the order of 2, codified by this amplitude of the ISW effect or amplitude of the ISW. But if you identify your voids in photometric samples, then in this case your voids are wide larger and typically elongated along the line of sight. And in this case, the mismatch between the expected value from Lambda CDM and what is measured is not only larger, 9 times larger, 10 times larger, but also quite imprecise. The error bars are quite large in this case. It has also been pointed out in the literature that the cold spot is an anomaly deserving of attention. And I'm not going to spend a long time on the progress on how this has evolved, just to mention that since its discovery, the discovery of this region in the CMB maps with a specifically cold temperature has been reviewed in the literature, and since the initial discovery, when they said, okay, this is around 4 sigmas of significance, if you take into account other effects, for instance, mask effect, mass selections, it gets less, perhaps, acute. One of the possibilities that has been proposed as a way to understanding if this is what is causing this cold spot has been precisely through the lensing of the ISW signal of a very large void around redshift 1. And even if the cold spot is statistically significant with just a fluctuation, a fluke, could be interesting to think if this could also be a signal hinting to something related to the ISW-void anomaly as well. So I don't want to mention it like this is attention. It's not. Could be statistically significant with just a fluke, a random fluctuation, but it could be interesting to think it as part of the same anomaly we saw previously. In the light of this H0 tension, sigma A tension, and these anomalies that I presented here, I want to bring back the questions that had been asked before. What is behind all of this? Can we just account for all of them by the proper understanding of systematics in our measurements? How much will it help to dissolve these tensions simultaneously? But how much do they also can be accounted for just by the proper understanding of the physics in the description of the observables? Somebody already pointed out to the paper by Radek Wojtak, or mentions the importance of taking into account the colors, the different color calibrations in supernovae that are local or not. It's just one example. But the point I want to make, which motivates our model, is can we unify these tensions and the explanation looking of new physics beyond the Lambda CDM model? And if we are going to do that, what path could we follow that tries to address them all simultaneously? As you may know, there's a number of models and proposals that have been raised fixing these tensions, in particular the H0 tension, due to the statistical significance that we have on it. Some of them do it by modifying the physics before recombination so that we can achieve a larger value of the H0, and they were already explained yesterday. Some of them require perhaps late time modifications. So instead of some early dark energy, they may appeal to some late dark energy, interacting dark energy models. To my knowledge, and the point I want to make here is that these solutions typically do not improve the tension in S8, for instance. Sometimes they actually worsen it, to my knowledge, but if somebody can correct me, I'll be more than happy. So the point I want to make is, can we look at the dark matter sector and find a solution that fixes is to the big word, but joins them and finds a solution for them that alleviates jointly? And why dark matter? Well, on the one hand, because it's dominant throughout a significant period of cosmic evolution, not to mention again the unknown physics behind the nature of the dark matter particle. We are not going to present here a particle physics model, a first principle model, but a phenomenological approach. And in this approach, we model the dark matter fluid through an evolving and non-zero equation of state, like many authors have done for dark energy before. We are going to impose that it has a strictly adiabatic speed of sound perturbations, speed of sound for the perturbations, and we are not saying anything about viscosity or other potential terms that could be accounted for in here. However, we're keeping the lambda term, so we still have a dark energy as a cosmological constant. It's very simple. You can see how now the equation for the evolution of the density of this dark matter will be modified by a function of time of whatever function you have for the equation of state. And the equation of state that we proposed, the simplest form we found, was such a value that you will have a dust-like solution at early times. So you fix this to have a 0, which is known in cosmology as dust. And after a transition redshift or scale factor, then you smoothly go towards a different value that's codified by this W0 parameter. So you have these two free parameters. When it happens, to what value it goes. There is a degeneracy between these two values and how they will impact your observations. By varying individually the value of this W0 or the value of the scale factor, we see that the change on the different observables we're going to investigate is degenerate. You can achieve the same change by increasing the W0 or increasing the redshift of transition, and it is a problem of a degeneracy that later on we will have to deal in when we try to sample this model with observations. So in order to break this degeneracy, we opted for fixing this, one of those. So we fixed the one that changes the least the observables, the transition redshift, to 1, which is a scale factor of 0.5. And then we will just investigate the effect of varying the value that codifies the negative equation of state for dark matter. This also imprints the way that the total matter evolves, the total matter density, which will be important when we want to look at the lensing signal, the lensing convergence, and the ISW signal that will be sensitive to the whole matter, not just the dark matter component. So in particular, you see that now you have this function of time. If it is dust or Lambda CDM, it's just trivially 1, and the time evolution should be trivially 0. But if not, then you have this evolution. How does it look like? Well, on the left-hand side, you can see that at the bottom plot, you have the redshift evolution and the equation of state. You can see clearly our choice of fixing the transition redshift at 1, and that before that, for all of this redshift, you have the dust solution, so you are consistent with Planck, with the late time with the early universe, and after that transition, you can go smoothly to a negative value to a positive value. If you go towards a negative value of this equation of state, then your Hubble diagram also acquires a larger Hubble rate, and then you can naturally reach a larger value for H0, like it has been shown in other proposals. But because it's on the dark matter sector, what you gain also is a decrease in the amplitude of your matter power spectrum. So as you reach negative values of your equation of state and increase your H0 tension, your H0 value, you also decrease the clustering that you get on the matter. And this is better exemplified on this sigma H parameter inset plot that you can see here. So naturally, you will couple these tensions by simply modifying, or these two values, by simply modifying what is the W0 value for this equation of state. Like I said, this also will affect the convergence of our lensing signals by having extra time-changing terms, and the ISW temperature in the way that the potential, the derivative of the potential changes or evolves in time, which is what you need for the ISW signal. It also carries this information from the equation of state. How does it look like now? The first effect you get is by achieving, you change the profiles in your temperature from the ISW effect. Like if you remember, this signal depends on what sample you have chosen to identify your voids. So the first one, which you get this spectroscopic sample for very spherical, small, well-behaved voids, you can see how you reach a lower value of the ISW temperature. And if you can see, I hope you can see on the larger plot, in larger screen, in this excess that codifies the departure from the expected value of Lambda CDM, now you increase your amplitude, and you lie within this gray band here that shows what is the observations, where should we aiming to. So now you can actually find an agreement with the observable range of the ISW, which is more pronounced for the photometric void sample because those are larger and more uncertain, but you can also achieve to lie within the expected value of this amplitude. And lastly, for these Eranidus voids that is supposed to be along the direction of the cold spot, which we can also find this potential to lie in the observed region of this extra ISW signal. So you have all of these three things put together. You get the lower clustering, the larger H0, and values that agree within the observed region of the ISW effect in voids. So now what happens if you try to constrain these three parameters using the observation that we have is a minimal extension. The first thing you can notice, we have all of the standard Lambda CDM parameters and the added parameter of this W0. For all of the parameters, you get fairly Gaussian, well-behaved posteriors, except for this W, which is the equation of state of the dark matter. If you only look at the Planck temperature, the Planck data, the temperature polarization, all of the data of the Planck 2018. But if you add more data sets to it, like C-phase from Pantheon, C-phase from SHUS and the Pantheon supernovae sample in BAO measurements, then we recover a value that is a marginalized posterior that is more Gaussian. It's centered around a negative value of minus 0.31, but within error bars, it includes the dust solution. And you can see how it changes now the difference between the H0 parameters that you can get. So now the tail of your distribution is consistent with a larger value of H0, and also you can achieve these smaller values of sigma 8. You obtain a better fit on the chi-square because you have a more complex model, but you will get penalized by it if you look at the AIC criterion, for instance. Lastly, like I said, we put by hand that the speed of sound of this model was 0, and this is how we run our modified class and everything else. And Magdalena, part of her thesis, is studying what can we gain if we relax this assumption. What if you don't put it by hand to 0, but you still keep the condition that it is adiabatic, so that the only component that matters is the time derivative of this. Immediately you will see that you have a function. It doesn't matter the function itself, but it matters that it depends on the equation, the parameters of your equation of state. And those can get negative. And for certain combination of these parameters, this number can get higher than 1, so higher than the speed of light. So without running anything else, just by looking at this and imposing that we don't want a speed of sound that is superluminous or negative, because that would be very unhealthy, we can just say, okay, these parameters are constrained to be within a range, within a region to be consistent with this. And as you keep increasing more constrictions, so how non-relativistic you want it to be, of course, you will converge to the dust solution, and then you get this degeneracy on the scale factor of the transition. Just for comparison, this dot with arrow bars is the value that we found in the previous analysis, which was derived assuming this to 0, so it's not consistent, but just to say it lies within a potential region of non-negative speed of sound values. So I'm just going to conclude by saying perhaps we can look at the ISW lensing anomaly as a source of detecting signals from modified physics in the dark sector. Could be a way of understanding these extra modifications we want to make. We have a negative dark matter model, so perhaps it's healthier to think about in the light of the interacting dark matter, dark energy dark matter models that were spoken before, which is better motivated than this. Of course, errors will shrink. We expect to gain more measurements in the ISW solutions. This is just a phenomenological model, but I think inspires certain search for other solutions. So thank you for your time, and I'm happy to take questions.
All right, let's do 2 questions. I see 2 hands, one here, one here.
Thank you, Mariana, for a wonderful talk. I have a question which is a bit out of context. So, can you tell me what kind of mass these dark matter have? Light or heavy?
No. Like I said, and perhaps I rushed through it, but in my mind it would be more useful to think about an interacting dark energy, dark matter model so that we can explain this has a negative equation of state, as opposed to thinking what sort of dark matter physical model could give you this behavior, because it would be very far-fetched in my opinion.
Yeah, so is there a way to detect these kind of dark matter? Do you have anything in your mind how to detect?
Not how to detect, but if you start playing with how structure grows in the universe, structure formation, and then you modify the dust-like solution, it will get imprints on how growth rate grows, and we can put restrictions on this by, for instance, redshift space distortion measurements and clustering on the F sigma 8 space. So there are a lot of constrictions, observational constrictions we can put if we carry on with the consequences of this modification, just to name one of them.
Thank you.
Thank you.
Thank you for the nice talk. My question is, to what extent one can think of this model as equivalent to a particularly designed dark energy parameterization, which would should keep the normal matter, and all the changes, you assign them to a new type of dark energy which corrects the cosmological constant. So you can think of it as a lambda, as a usual, not usual, but a properly designed extended dark energy model. Is it possible, or some genetic feature which prohibits us from seeing this in this way?
I don't think we are. I think it's a wonderful idea. It's actually something we're thinking of doing. How could we replace this and say, this is not dark matter that's negative, but this is an effective equation of state for these coupled fluids, fluid X, fluid X2, where the dark matter is dust, it's just cold dark matter, but the interaction rate between the two fluids is the culprit for this behavior that effectively does the phenomenology that we liked about it. I have not done this yet, so I can't answer how it looks like, but it's very tempting to research this idea. Thank you.
So I have one question. So it seems like the value of A and Z is very important, actually, because, but you fixed it to some value. What happens if you change that value? Have you tried that?
Not yet. For convergence reasons, this would not converge if you let them vary freely, because you saw the degeneracy you will get in your observables. So we chose to fit it just to a single value. Now we would like to do the 2 changes to properly take into account this. On the one hand, you can put restrictions to what values are allowed within these conditions of a physical speed of sound value. And then we would need to rerun the chains to see now, can we break that degeneracy and let them vary freely? We expect that this will impose now the opposite. We will have very penalized values for the W naught, very dust-like, and then trying to impose a constraint on the transition redshift as a result. But we haven't fully accounted for the non-zero speed of sound in the Boltzmann solver yet.
But you didn't like try, I don't know, just setting it
Just
to
we
0.4
checked.
or something and see what happens.
Not that I recall. Maybe at the very early stages, but nothing significant was caught our attention.
Was there a reason for choosing the number you did, or just as a wrong number?
Just as a motivated, say, where we expect to see some effects of this modification is late enough, we can put some constraining from data on this region. So it was from a theoretical side, not motivated by how the model behaved on a statistical level. But thank you. Thank you.